Hello everyone, my name is Nathan Klammeesri. My student ID number is 6610750223 and I'm from the Mechanical Engineering Department.
Hi, my name is Weraphat Piyawong. My student ID is 6610750355 and I'm from the Mechanical Engineering Department.
Today we will be presenting about the RC Circuit Lab 6 that we have completed in our LE203 course.
So let's proceed to the introduction to the experiment. This experiment involves analyzing the behavior of a series RC circuit, a resistor capacitor circuit, in both charging and discharging conditions. This is a fundamental topic in circuit theory and electronics, and is essential for understanding how capacitors respond to voltage over time.
The key objectives of these labs are first to observe and measure the charging and discharge of behavior of a capacitor in a RC circuit. Second is to analyze the voltage across the capacitor over time. And lastly, to compare experimental results with theoretical predictions using the RC time constant formula. So part 1, we will do DC and AC voltage measurement. So here is the circuit diagram in which we are gonna do, and we will need some equipment. Here are the lists. We will use multimeter, some wires, a resistor 3.3 kilo ohms, an oscilloscope, some probe wires, connectors, AC source, and DC power supply. So the first step is to connect the multimeter to the DC power supply by using the wires and check for the multimeter to be 2.5 volts. After that, we will connect the DC power supply to the oscilloscope, 0 volts. Then we will use another wire to connect to the 6 volts of the oscilloscope to the point A of the resistor. Then point B of the resistor, there will be another wire connected back to the DC power supply. Then we will use the oscilloscope. We will use the probe wire to connect to channel 1 to the point A of the resistor and the ground to point B of the resistor. And on the oscilloscope, we will press the auto set button and set the scale to 5 volts, and here will be our diagram. So here is the overview of the circuit if done correctly. You can see here the wires connected to the power supply and connected to the multimeter 2.5 volts, then to the AC source on the 0 and 6 volts. Then they will be connected to the 3.3 kilo ohm resistor like this, as shown here. Probes also connected, channel 1 and ground, on point A and B. And here is the oscilloscope on the channel 1, and here is the diagram.
So we adjust the channel to DC. Here's are the result in the graph we get. For the result, we get 5 voltage per division as we mentioned before, 3.8 peak to peak divisions, and 19 voltage peak to peak. For the time, we get 10 milliseconds per divisions. The period is 2 divisions, so the period is 20 milliseconds. And from the period, we can get a frequency. Frequency is 50 Hz. And here's are the graph and the result we get when we adjust the channel to AC. As you can see, the result is exactly the same, but the difference is the graph.
So for part 2 is phase shift measurement. Here is the diagram that we're gonna do. the equipment is almost the same as part 1, but we do not need a multimeter and DC power supply for this one. And we also need 2 probe wires instead of 1, and the resistor we will change to 1 kilo ohm and another 1 mil flux. So for the first step, we will take a wire and plug it into the AC source of 9 volts, and the end of the wire we will put in the resistor of 1 kilo ohm. Then we also take another wire, put into the 1 kilo ohm of the other side, and then plug it into the capacitor of 1 mil F on the plus side. And another wire on the minus side goes back into the AC source of 0 volts. Next, the oscilloscope. We will take the 2 probe wires, plug in the first probe wire will plug into the channel 1, and at the end of the wire will be on point A, point 1. Then the ground will be on point 3. For the second probe wire, plug into the channel 2, and at the end of the wire plug into point 2. And the ground, same as the channel 1, plug into the point 3. On the oscilloscope, we will also need to press auto set. And when we press auto set, the 2 waveforms will be on top and the bottom. We will need to move the scale into the middle, and we will get this result. And for the channel 2, we will also need to press the invert button to make it inverted. So here is the overview of the circuit. As you can see here, the AC source is connected to 2 wires. The red wire is connected to point 1 and yellow to point B. And you can see the connectors on top of the wires, so we can connect the probe wires from channel 1 and 2 on the oscilloscope. If you connected it correctly, it will be right here.
As you can see in the oscilloscope, the yellow waveform is for the channel 1 and the blue waveform is for the channel 2. So let's talk about the channel 1. We adjust the voltage scale into 2 volt, so we can get a 2 volt division, a 4.4 peak to peak divisions, and we can get a voltage 8 to 8 peak to peak. For time, we have 10 millisecond divisions. The period is 2 divisions, so the period is 20 milliseconds. So from the period we can get a frequency which is 50 Hz. Let's move on to the channel 2. We adjust the voltage scale to 10 voltage, so we can have a 10 voltage divisions, and the peak to peak is 2.8 divisions, so we can get a voltage 78 peak to peak. So for the time we have 10 millisecond divisions, the period is 2 divisions, and we can get a period 20 milliseconds, and the frequency is from the period which is 50 Hz. To measure the time shift, as you can see, there is a gap between 2 waveforms which is equal to 1 division or 5 milliseconds. So to calculate the phase shift, we need to use the time shift divided by the period and multiply by 360 degrees. So from this experiment, we will get the time shift is equal to 5 milliseconds and the period is equal to 20 milliseconds, which is divided, and we will get 1 divided by 4 and multiply with 360, we will get a 90 degree.
Next is our discussion and analysis. We compared the experimental data to the theoretical voltage curve for both charging and discharging phases. The results show that the capacitor voltage increased gradually at first and then more slowly as it approached the supply voltage during charging. Similarly, during discharging, the voltage dropped quickly at first and then leveled off. Our measurements closely followed the expected exponential trend, which indicates that the circuit behaved as predicted. Any small differences between the measured and theoretical values could be due to factors like slight inaccuracies in component values, signal noise or measurement delays from the oscilloscope, or the imperfections in the connections on the breadboard. Despite these small variations, the experiment successfully demonstrated the typical behavior of an RC circuit.
So here's the conclusion. To wrap up, this lab helped me clearly understand how an RC circuit behaves in both charging and discharging conditions. Seeing the voltage across the capacitor change in real time on the oscilloscope made the exponential behavior much easier to guess than just reading about it in theory. It also showed me how small things like component tolerances or connection quality can affect circuit performance. Overall, this experiment reinforced key concepts about energy, storage, and time-dependent responses in circuit, which are important in many real-world applications like filters and timers.